So today I'm going to be showing you how to solve example 2C1 in our dynamics textbook. So what's given is that we have a velocity at b that is going to the left at 5 meters per second. And we know that this point here, because it is a stationary surface and is no slip, we know that this is going to end up being 0. And we can rotate this to give us a right angle triangle that we know all three sides of. And we're going to call this base D, which is just the square root of L squared minus R squared. So step 1 is for us to use our velocity equations. So we know that, and I'll move my hand once I get this written down, we know that the velocity at A is equal to the velocity at B plus the angular velocity of AB crossed with the radius of A slash B. And now we can go even further into depth. So we know that velocity of A is equal to, and we know that velocity of B is going to the left, so it's equal to negative VB in the I direction plus the angular velocity of AB in the K direction crossed with, and we know here that the radius is negative D in the I direction and R in the J direction. Now if you go ahead and do that, it gives us that VA is equal to negative VB in the I direction minus, and K cross I gives you J, so it's minus D times the angular velocity of AB in the J direction minus R times the angular velocity of AB in the I direction, because K cross J gives you I. So now that we've done the velocity equations between A and B here, now we need to do it between A and C. So we know that the velocity of A is equal to the velocity at C minus, no, my bad, plus the angular velocity of the wheel, which I'm going to shorten to W, crossed with the radius of A to C. And now we can break this down into the components. Velocity of A is equal to, and remember, because this is no slip and stationary, the velocity at C is equal to 0. So VA is equal to 0 plus the angular velocity of the wheel in the K direction crossed with, and be careful here, it's not just the radius in the one direction, it's the radius in the I direction and the radius in the J direction. And then this can be broken into R times the angular velocity of the wheel in the J direction, because K cross I is J, minus R times the angular velocity of the wheel in the I direction. So now we have two equations for A, so we can group up the components here. So we know in the I direction that negative VB minus the radius times what angular velocity of AB is equal to negative angular velocity of the wheel times the radius. And in the j direction, negative distance d times the angular velocity of AB is equal to the radius times omega of the wheel. So now here we can rearrange and solve for omega of AB, which is equal to negative radius over distance d times the angular velocity of the wheel. Now we can plug this into the I equation to get negative VB minus the radius times negative r over d times omega of w is equal to negative omega of the wheel times r. Now we can add this to this side, so we know that negative v of b is equal to the radius squared over negative d times omega w minus the radius times omega of w. Now we can factor out this omega w. So we know that negative VB is equal to angular velocity of the wheel times negative r squared over d minus r. Now we can divide this over, giving us that angular velocity of the wheel is equal to negative velocity in the b direction, negative velocity of b over negative r squared over d minus r. And if you plug in the values that you were given at the beginning, you're given that negative 5 over negative 0.5 squared over the square root of 2 squared minus 0.5 squared, all minus 0.5. So we know that omega of the wheel is equal to 7.95 feet per second. So there's the first one. So now it's time to move on to the acceleration equations. So again, we're going to start with points A and B. So we know that the acceleration of A is equal to the acceleration of B plus the angular velocity of AB crossed with the radius of A slash B minus angular velocity of AB squared times the radius of A slash B. Okay? Now this breaks down into components. So acceleration of A is equal to 0 plus the acceleration of AB in the k direction crossed with, again, you got to be careful with this one, it's negative d in the I direction and r in the j direction minus angular velocity of AB squared times parentheses negative di plus r of j. Okay. And now we can go ahead and do the cross products. So we know that the acceleration of A is equal to 0 minus distance d times the angular acceleration of AB in the j direction minus the radius times the angular acceleration of AB in the I direction plus angular velocity of AB squared times distance d in the I direction minus angular velocity of AB squared times radius in the j direction. So here's your first acceleration equation. Now we need to do the second acceleration equation for A. So the acceleration of A is equal to the acceleration of C plus the angular velocity of the wheel, which again I'm just shortening to W, crossed with the radius of A slash C minus angular velocity of the wheel squared times the radius of A slash C. Now we're going to break this into components. And be careful here. Just because the velocity of point C is 0 does not mean that the acceleration is 0. So we're going to write this as acceleration of A is equal to the acceleration of C in the j direction, because we know that C is going to be moving upwards. Plus the angular acceleration of the wheel in the k direction crossed with, and again, it's radius in the I and radius in the j. Minus the angular acceleration, angular velocity of the wheel squared times the radius in the I plus the radius in the j. Now we can go ahead and do the cross product, which gives us that the acceleration of A is equal to the acceleration of C in the j direction plus the radius times angular acceleration of the wheel in the j direction minus the radius times the angular acceleration of the wheel in the I direction minus angular velocity of the wheel squared times r in the I direction minus angular velocity of the wheel squared times r in the j direction. Now, we have three unknowns here, so we need to figure out an equation to solve for one of them. So we're going to try and figure out the acceleration of C. So we're going to use 2 points that we know, which is point O and point C. So the acceleration of O is equal to the acceleration of C plus angular acceleration of the wheel crossed with radius of O slash C minus angular velocity of the wheel squared times the radius of OC. Again, we're going to break this into components. So the acceleration of O in the I direction is equal to the acceleration of c in the j direction plus the angular acceleration of the wheel in the k direction crossed with the radius in the j direction minus angular velocity of the wheel squared times r in the j direction. So now we can go ahead and do the cross product. So we know that acceleration of O in the I direction is equal to acceleration of C in the J direction minus angular acceleration of the wheel times R in the I direction minus angular velocity of the wheel squared times R in the J direction. So now that we have all three equations, we're going to group up the I components and the J components once again. So for the I components, for the acceleration of A and O, of C and O, we have that acceleration of O is equal to negative R times the angular acceleration of the wheel, and in the J, which is what we really care about, that 0 is equal to the acceleration of C minus R times the angular velocity of the wheel squared and this allows us to solve for acceleration of C, which is equal to the radius times angular velocity of the wheel squared. Now we're going to use this. So we're going to plug AC back into our two acceleration equations for A set equal to each other, which gives us negative d times the angular acceleration of AB in the j direction minus the radius times the angular acceleration of AB in the I direction plus distance d times angular velocity of AB squared in the I direction minus the radius times angular velocity of AB squared in the j direction is equal to the radius times angular velocity of the wheel squared in the j direction plus the radius times the angular acceleration of the wheel in the j direction minus the radius times the angular acceleration of the wheel in the I direction minus the radius times angular velocity of the wheel squared in the I direction minus the radius times angular velocity of the wheel squared in the j direction. Okay, now that we have this, we can once again group up the I and the j components. So for the I, we have negative radius times angular acceleration AB plus distance d times angular velocity of AB squared is equal to negative radius times the angular acceleration of the wheel minus the radius times the angular velocity of the wheel squared. And that's our I component. Now for the J component, negative distance d times angular acceleration of AB minus radius r times the angular velocity AB squared is equal to the radius times the angular velocity of the wheel squared plus the radius times the angular acceleration of the wheel minus the radius times angular velocity of the wheel squared. So the r times angular velocity of the wheel squared cancels out on this side. And from here, we can start to rearrange the equations, solve, and substitute in to solve for our angular acceleration of the wheel. So first things first, we rearrange the equation for the J components to negative d times angular acceleration of AB is equal to the radius times angular velocity of AB squared plus the radius times angular acceleration of the wheel now we rearrange this and get the angular acceleration of AB is equal to negative r over d times negative r over d times angular velocity of the wheel squared plus radius over negative d angular acceleration of the wheel. And from here, we can plug in what we know back into the I equation. So we know that negative radius times the negative r over d times negative r over d omega of the wheel squared minus radius over d times the acceleration of the wheel plus d times negative r over d times the angular velocity of the wheel squared is equal to negative r angular acceleration of the wheel minus r angular velocity of the wheel squared. Now we start to FOIL out the radius into these parentheses, which gives us that radius squared over d times negative r over d omega of the wheel squared plus the radius squared over d times acceleration of the wheel plus d times negative r over d omega of the wheel squared is equal to negative r times the acceleration of the wheel minus r times omega of the wheel squared. Now, we need to rearrange this to get the accelerations of the wheel on the same side, which gives us r squared over d times negative r over d omega of w squared plus d times negative r over d times omega of w squared plus the radius times angular acceleration of the wheel squared is equal to negative r squared over d angular acceleration of the wheel minus radius angular acceleration of the wheel. From here, we can pull an angular acceleration of the wheel out from the right side, leaving us with radius squared over d times net radius over distance d times angular velocity of the wheel squared plus distance d times negative r over d times angular velocity of the wheel squared plus radius times angular velocity of the wheel squared is equal to angular acceleration of the wheel, parenthesis, negative r squared over d minus r. From here, we can divide the negative r squared over d minus r over to the other side, giving us that the angular acceleration of the wheel is equal to, and here we can pull out the negative r over d times omega of w squared, leaving us with r squared over d plus d times negative r over d times omega of the wheel squared plus radius times omega of the wheel squared all over negative radius squared over d minus radius. And if you plug in the values that we have been given and that we have solved for, it gives us that the angular acceleration of the wheel is equal to negative 116.8 feet per second squared. And that is how you solve this problem.